Hi, welcome back to the course Computer Vision from Scratch. Today's lecture is completely dedicated to learning a platform called as weights and biases. The reason why I am introducing this to you is because in the rest of the course, we will be conducting a lot of ML model experiments by changing hyperparameters. And this will cost you a lot of time, and you would want to optimize the process of conducting these experiments, making it very systematic, noting down the results of these experiments. If you are changing the, let's say, learning rate or batch size, or if you are cropping the images in a certain way, all of these constitute separate experiments. And you want to see how the classification accuracy changes, how the loss decreases. All of this you want to note down properly, and doing it separately by manually changing the hyperparameters and noting down the results in an Excel sheet is not the way to go. So this lecture, irrespective of whether you are a computer vision enthusiast or not, this is going to be very, very helpful for you throughout your machine learning journey. And today you will learn how to actually conduct ML experiments like an actual professional who's working in ML. So this is an introduction to weights and biases platform, not the typical weights and biases that are part of the neural network. This is the name of a platform. So I'll be introducing you to this. And it's going to be very easy, nothing fancy, nothing that you have to be worried about. And you will learn proper practical skills by the end of this lecture. So let us get into the lecture. Welcome back once again to the course. So before we get into the lecture content, let me keep reminding all of us that there is a reason why we have started learning computer vision. It is to master this whole area, which is a vast area of practical machine learning skill. So we want to invest good amount of time in this whole series. So starting something is easy. As I have shown you, this graph represents how a typical playlist progresses for various reasons, of course. But if you have started this series, I highly recommend you to travel with me and finish this. And we will all have a very good learning experience at the end of this. So let's take a pledge that we will finish the series, since we have started this with a very good reason, and try to find a friend or acquaintance who is interested to learn with you, so that mutually you can keep yourself responsible or accountable. Or you can even put a comment so that you are publicly making yourself accountable for finishing this series. But with that, let's have a brief recap of what all we learned so far in this course. So we built a 5-class classifier, which allows us to classify these flower datasets. So this is 5-flower dataset, very famous. It's available on Kaggle and various other platforms. Daisy, dandelion, roses, sunflowers, and tulips. So we have 5 category of flowers, and we are building machine learning / deep learning models for making classification of these flower images. So far, we have built 2 models. First was a linear model. So linear model meaning it was like a neural network, but just input and then converting that input into a linear flattened layer. And this flattened layer is converted into an output. We constructed this linear model, and we found that the loss is of the order of something between 10 and 20. And accuracy, especially if you look at validation accuracy, it's on the order of 0.5. So it's half. We also discussed that a worst classification model for a 5-class classification will not have a 0% accuracy. It would rather have a 20% accuracy, because a worst model is like a monkey choosing randomly from one of the 5 classes upon seeing an image, right? And there is a 20% chance that the monkey can be correct. So just like that, an ML model, which is performing its absolute worst, should be 20% accurate. So this linear model, although it's not very good, we saw that it had 45-50% accuracy. Not bad at all. But please note the order of magnitude of the loss here. It was between 10 to 20. Then we built an actual neural network in the previous lecture. Here what we did was we added an additional hidden layer. This hidden layer had certain number of nodes. To be specific, it had 128 nodes. And this hidden layer, with this hidden layer, we were hoping that we will have a better classification. We used ReLU activation, rectified linear unit activation after the hidden layer. And we were hoping that this will introduce some non-linearity in the model, which will allow us to learn complex patterns in the image. So it indeed reflects in the loss. So you can see that the loss has decreased by almost an order of magnitude. So previously the loss was between 10 and 20. Now it is clearly between 1 and 2, somewhere around that range. So loss has decreased by an order of magnitude. However, accuracy, especially validation accuracy, did not see tremendous improvement. It is still on the order of 0.45, 0.5, etc. We can also see from this specific graph that the validation accuracy started to decrease after a certain point. And this is a classic sign of overfitting, because training accuracy is increasing and validation accuracy is decreasing, right? So all of these were assuming certain parameters, certain batch size, certain image dimension, certain learning rate, or certain number of nodes in the hidden layer, etc. So we discussed in the last lecture that we wanted to change a few of these parameters. Like we wanted to change the learning rate. Maybe trying to make the learning rates lower might help us learn things better, or increasing or decreasing the number of epochs. We can see what effect epochs had on the classification accuracy, especially the validation accuracy. We were looking at learning rate. Looking meaning we were discussing that. We did not, of course, change all of these hyperparameters, but let me write it down here. So learning rate, epochs, then there is batch size, then there is nodes in the hidden layer, and then image height or width. Image height or width, one of them, right? So these are some of the hyperparameters that we were interested in changing. And in the last lecture, actually, if I open the notes, I'll show you the graphs that we had. So here we ran different set of experiments. Here the image size was 224 pixels by 224, batch size was 16, learning rate 0.001. And we discussed in detail the results we got. Then we tried with different image size, different batch size, etc. So we ran set of 4 experiments here, and a bit more number of experiments that are not shown here in these set of graphs. So this is what we did in the last lecture. And what I wanted to do in this lecture originally was just to play with the learning rate and few more number of hyperparameters, and then show that the model is actually overtraining, and we wanted to implement something like regularization, dropout, etc. So we discussed that briefly towards the end of the previous lecture, that in the next lecture, we will try regularization, dropout. We may try building a deeper neural network, meaning more number of hidden layers, etc. But I also realized that the way we are building these experiments, the way we are constructing these hyperparameter tuning is like a caveman. Because what we did in the last lecture was we had a code in which hyperparameters were there, right? Epochs, learning rate, etc. Then to execute the code, even for 5 epochs, it was taking some time. On my system, it was taking at least 15-20 minutes per experiment. So what I did was I have a few different Google accounts. So I have few different Google Colabs, which can be accessed through those different Google accounts. So I was copy pasting the exact same code and just changing the hyperparameter value, epochs or learning rate, etc. And I was running these codes parallelly. So copied the same code to multiple Colab accounts, manually changed the hyperparameters, ran them separately. This caused me a lot of issues also, because if you manually change the hyperparameters, you have to be very diligent. You're not sure if you are running the same experiment twice. You don't want to do that. You want to run different experiments ideally. And then I was also saving the final outputs manually in an Excel sheet. So this was a very primitive approach. There are even better approaches that we actually do in production level machine learning pipeline. So when we partner with companies, we never do things like this. This is a very caveman kind of approach. There are smarter ways to do this. So I want to dedicate this entire lecture towards teaching you how to conduct these experiments in a very, very streamlined professional fashion, but without increasing any kind of difficulty in your coding or in your whole process. I will show you this, and this is through this platform called as Weights and Biases, so that we are not going to be consuming a lot of time copy pasting code and running different Colab environments. We won't make error of duplicating the same experiment and running it. It's obviously not scalable. What if you want to try 15 different hyperparameters? Are you going to write a for loop and run the same Colab notebook? And then you wait for the results, and are you going to note down these results manually somewhere else, or are you going to do something else? How do you track and compare your results in your different experiments? Are you going to copy paste your results into Excel sheet and make plots, right? So there are so many things where this whole process of manual ML experiment conducting is very primitive. So this is where hyperparameter using weights and bias come into picture. I will of course show you weights and bias website very soon, and this will be a skill that will, I'm pretty sure, with weights and biases or with any other platform which allow you to conduct ML experiments in a much more professional fashion, this skill will stay with you forever. And even if the platform of popularity in the future is not weights and biases, if it is something else, it's okay. You will still remember that when you're conducting these experiments, you have to perform it in a systematic way. And I will show you what the weights and biases can do. So before I teach you weights and biases, let me first show you some of the results I have from some experiments. So this is the weights and biases platform. They also have amazing courses. Feel free to check out. But we have already created an account here for Visuara. So some of the projects that we have done in the past are on this platform only. But I'll show you the specific five flowers dataset project that we are currently doing, right? So this is the recent run that I had done literally yesterday. So here, what you can see is this is a plot of validation accuracy on the y-axis and epochs on the x-axis. So let me just expand this. Here, what you can see is this is the result of all these different experiments. These numbers denote batch size. So 8 is the batch size. 10, if I remember correctly, it's okay. 128 is definitely the number of nodes. 16, I think 16 and 32 are some other hyperparameter. 0.001 is the learning rate. So I'll explain this systematically to you. But what you want to notice here is like these plots are the results of various different experiments I conducted. And I did not even have to manually log any of this here. All of this happened automatically with just few lines of code, additional code in Google Colab. So I will show you how exactly to connect Google Colab to weights and biases, how to run your experiments in a much more modern fashion, how to get these results. And this result can actually be also converted into a proper project report. So I have a sample project report here. Let me show you. So if I open this project, you will see a section called reports over here. And I think this is the first report. This is the report which I have titled and created. So here you can, if you want to share a report like this to anyone, let's say you are submitting some assignment or you are working with a client in your company, this is a great way to show them a demonstration of the experiments which you have performed. Let me increase this a bit. Yeah, and it's interactive also. These plots are interactive. I know it looks overwhelming because there are a lot of numbers going on here, but I'll simplify all of this for you. So don't worry about this. So this is the weights and biases platform. So I'll first introduce you to this. I'll show you how to connect, and I'll show you how to run your first experiments and log your first experimental results in weights and biases, so that this will help you throughout your rest of the computer vision course as well as your machine learning journey. So weights and bias basically allows you to conduct and track your experimental results. You can compare your different models, how the results are. You can conduct a hyperparameter sweep, and you can log many different experimental parameters, validation accuracy, loss, training accuracy, many other things. And it also supports TensorFlow, PyTorch, Keras, everything. So let's actually open weights and biases once, and then let's run a set of experiments, right? So this is what you will see when you Google weights and biases. Open this, and now what they see is AI is hard to productionize. It's not hard, it's easy. So what do you mean by production level AI? It means making AI models and then making it as close to deployment as possible for solving some problems, right? And for that, you have to train the AI model, you have to optimize the hyperparameters, and for that, you will have to conduct a lot of experiments. We will be invariably doing all of this in the computer vision course as well. So you will have to create an account by signing up. I think there are two options, personal account or company account. So if you are an individual, you can create a individual personal account. So let me try over here. So here, if I go to weights and biases. I don't have an account on this Google account. So here, if I click sign up, they will ask us to fill a form. So you can fill all of this and you will have access to weights and biases. So you can fill things here, right? So if you're using it for academic use or professional use, you have to verify that. If you are a student, you can, I think they might ask you for your email ID for your college or .edu email ID. Just check that. We got it through professional account. So I'm pretty sure most of you will be able to have this account either through your company or through your educational institution. And once you have the account, what you have to do is you can go to this section. So platform or get started with models, you can click here and this will ask you to create, and in quick start it will ask you to create weights and bias pip install in your Python. So what you have to do is, if you are on Mac, go to terminal, or if you are on Windows, go to command line interface, and then you can copy paste pip install weights and bias W and B. Just copy paste here and press enter. So this will install weights and biases in your system, weights and biases library in your system. I already have this, so I don't have to do this necessarily, but it might show requirement is already satisfied, as you can see here. And then you can do weights and biases login. So in the login, there is one specific thing that you have to note. I'll show you. So here, click login. They will ask you for an API key. So the API key you can get from your specific project. So here we have a specific API key. I will show you where to find that, find your API key from. You have to copy paste that here. So what you can do is you go to weights and biases projects. And if you don't have a project, you will have to create one. So here, assuming you have an account, I'm going to log into our account. So here, login, and using the Google account, you can do the login. And once you log in, you will be in the home page corresponding to your particular account. In an account, you can create multiple projects, and you can also share it with other people, share the project, or you can have multiple users using the same account. So here in our account, we already have multiple projects, but if you want to create a new project, you can click new project, right? So let's actually do that. Click new project, and it will be in our team. So we have this team, and let's say 5 flowers new. So that is the name of my project. And here I will say visibility is only to the team members and create project. So this will create an empty project. Inside this project, there will be nothing. There will be no report. There will be no logged data, nothing, right? Because it's empty. So here you can select W and B models instead of W and B weave. So go to this models. And if you remember, we are currently running our code in Keras TensorFlow. So here, visualize your model training using Keras TensorFlow that you can select. You don't have to open this in Google Colab right now. I'll show you an even simpler way. So we already did pip install W and B and we typed login, and then we had to paste the API key. So this is where you will find the API key in this page. You can copy it from here and go to terminal, and you can paste it. But since I'm already logged in, I can maybe type W and B login dash relogin. So this will force me to paste my API key so that I can show you the step. And then here I pasted it already, but you can't see it because it's private. But now I have successfully logged in, right, using my API key. So this is what you also have to do. And then we can go to Google Colab. So let me open Google Colab code, which we had earlier. So this was the, not this, this was the Colab code we had earlier. So in the code, we defined everything manually. Manually meaning we had fixed hyperparameters, image height, image width. So this was originally 224. And in our experiments, we changed it to various numbers, 64, 16, etc. These are the 5 classes. Then we read the CSV file and we created images and corresponding labels. That is here, image and label. Then we created the training data set from this CSV file link. We created the evaluation validation data set also from this evalset.csv file. And then here we were printing the batch size. So batch size was 16. and image size was 16 by 16 by 3. It's 3 channels because there is red, green, and blue. And here, these are the labels. So 0, 1, 2, 3, 4 means 0 means this one daisy, 1 means dandelion, roses, sunflowers, tulips, like that, 0 to 4. And then we defined our neural network, right? So we had first the flattening operation. So image, which was 224 by 224 into 3 RGB channels, was converted into one single flattened input. So if 224, 224, 3 is the image dimension, the flattened layer will have 224 multiplied by 224 multiplied by 3. Then there was a dense layer, which was fully connected connections from the flattened to the hidden layer. This 124 nodes, and then it has a ReLU activation. I already mentioned this. And the last layer was simply a 5-class classification layer with a activation of softmax. But technically, this is just for converting your final output into probabilities, right? And we used Adam as the optimizer, and we were optimizing for accuracy. Then most of our experiments were for 5 epochs. Here you can see that the validation accuracy finally was around 0.45, 0.46, in that range. And then we also plotted the loss versus epoch, or accuracy versus epoch. So this is in a nutshell what we did. Now what we want to do here is we want to convert this code into something that is friendly for the weights and bias platform. Meaning, first we have to connect this to weights and biases, and then we also have to define how we are going to perform hyperparameter sweep. Like how can we conduct set of a bunch of different experiments with different image heights, with different batch sizes. So here this 16 is the batch size. How can we conduct experiments with just one set of code? And how can we log all of these results into weights and biases platform so that we don't have to sit in front of computer, let the running finish, let the logging finish. We can come back, but instead of opening everything on Google Colab, we can open weights and biases and see which model, which hyperparameters have given you the best output, right? So this is what we want to examine. So let us do first thing, import W and B. So this is the weights and bias import. Now, because we are integrating Keras, TensorFlow Keras into weights and bias, we can say import W and B dot integration dot Keras. From this import, we have two things to import: WNB metrics logger and WNB model checkpoint. So import WNB metrics logger and WNB model checkpoint. So this is just to we can use this as while running the different epochs. And then, of course, we are importing TensorFlow. We are also importing Keras somewhere later. So this piece of code I can bring here so that all imports are in one place. All right. And let me also do one thing. Let me split the code such that this part of the code I can include later. So all the imports can be in one block, and we can define another block for rest of the things. All right. And let's also run this code to make sure that our import of weights and biases, or W and B, WNB. All right, so this should hopefully work now. Okay, so our code is working. Now we need one more block for initializing the weights and bias configuration. So here we can define sweep configuration. So we are doing a hyperparameter sweep, and inside this we have to define the method, metric, and parameters. So method equal to something. We can do grid search. Metric equal to, and here we'll have two things. One is goal and parameters. And in the parameters, we will define all the different hyperparameters that we want to work with, right? So this metric will have name and goal. So this part is, although it may look unfamiliar, it's straightforward. Here it should not be equal to, here it should be colon. And goal is validation accuracy, and or name is validation accuracy, goal is to maximize. All right. And parameters, we have what all we have: batch size, batch underscore size. And here also we can define multiple batches. So multiple batch sizes. So values, and values could be, let's say, batch size 8 and 16. Then we can have learning rate. Learning rate values could be 0.001, comma 0.0001. So this is learning rate values. Then we have hidden nodes, basically the number of nodes in hidden layer. It could be 128 and maybe 64. So this is purely empirical, right? I have no idea which one works really well. So I have to try a few different things. So that's why I'm giving a lower value and an upper value. Then we can do image size. So img size equal to values. We have 224 and let's say 16 by 16. So 224 by 224, that's the first size. Since height and width are the same, I don't want to define both height and width. So I'll just say one thing, image size. And I think that's pretty much it, right? Is there any other hyperparameter? Batch size, epochs, yes. So epochs is values, and number of epochs could be 5 or 10. So these are our parameters. This is our sweep configuration. So grid search, meaning we will have a grid of these hyperparameters. So one set of hyperparameter could be 8 batches, 0.001 as the learning rate, 128 hidden nodes, this as the image size, and this many epochs. And there will be so many such combinations possible. So if there are 2 values for each hyperparameters, and if there are n hyperparameters, there are 2 raised to n possible experiments to run. So we define the sweep configuration like this. You can name this as whatever, does not matter. All right. Now we say, let's say sweep ID. We just define an ID equal to weights and biases dot sweep of. We are sweeping for this sweep configuration, and we have to provide the project name. And project name is, we can check this in our weights and biases dashboard. We created a new project. I think it was called 5 flowers new. Let's check. So here in the dashboard, we can go to projects section, and here you should see so this is the name of the project, 5 flowers new. All right. So let's go back to that. Now this block is now ready. We can try running this to see if there are any errors. All right. So so this is working. And here it has created a sweep URL. So sweep URL will allow us to, this is the URL which will allow us to track all the experimental results. So I don't think it will open publicly. We have to be logged into our particular account. So I'll go back, and here I can just, copy paste this URL, because since I'm already logged in here, it should open hopefully. So so it is opening, and this is our project. And here you don't see anything here. It's completely empty because we haven't even run a single experiment, right? So that is what we are going to do next. So then we say, let's define a new block. Here we can define a function called train, define train. And here with W and B, okay, here already I am getting the right suggestion with W and B dot init. So this initializes weights and biases library, and as run with this as run, config equal to wnb.config. So what does this do? wnb.config will give us basically these parameters in the configuration. So we'll be able to access that. And with this as the configuration, now we can define our rest of the code inside this function. So I'm cutting this instead of copying. Let me cut this and paste it here. But of course, it has to be inside the function, which function inside the train function. So I have to add indentation. So let me add the indentation, appropriate indentation. And I'm also going to eliminate a few things that I don't need. I don't need to print the batch size. So this I'm going to delete. And then this is the part where we define the model. So that also we can paste. So this is the model definition and model.compile. So previously it was history equal to model.compile and we were printing it. Now we don't need it. So history part has been removed. Yeah, so this is the history, right? So model.fit. Okay, not in the model.compile, in model.fit. All right, so that part is also good. Okay, so now there are a few things you might be wondering, okay, but we are yet to define epochs. We are yet to define the rest of the things because right now it's all hard coded. Image height, everything is hard coded. We are not fetching anything from here yet, right? So let's do that. But before that, let me clean up the code. Let me delete this. We don't need the history. I'll delete this. I'll delete this. This also I will delete. Okay. Now let's go one by one. Maybe we can go from the bottom, or actually this we can start. So this will be config.img size. Why? Because in our configuration, img size is the name of the image size. So here we don't have to explicitly mention values. It will be fetched automatically in the grid search. Then image width also should be img size. Number of channels are fixed 3 RGB channels. Now the class labels are also fixed, so nothing to change here. Then we have to, I don't think we have to change anything else. Image height and width are already defined. Then everything in this code, nothing to change. This is all from the past lecture. Okay, here in the batch size, config.batch_size, right? Where is the code? Yeah, batch size, that is fine. And here also, this is the batch size for the training dataset, train dataset. And this is the batch size for the validation dataset. So that is also then now defined. Now, number of nodes in the hidden layer. So this should be batch.something. I think it's called batch.hidden nodes, right? So batch.hidden nodes, let me put it here. Yeah, here. Number of hidden nodes, activation will be ReLU. Everything else is fine. Optimizer is Adam. Loss function is this. Metrics is accuracy. All of that is correct. Then epochs will be batch.epochs. Epoch. So we also, because we also have a epochs in this epochs term in this in the batch parameters, right? So that also we define. And then we have to have a callback here. So what we can do is comma. And then here we can paste the callbacks. So here is where the logger, the weights and bias metrics logger is used. And in fact, in one of the earlier imports, I don't think we need to import this separately. We just need the WNB metrics logger. The other one is not needed. So we can just run this. So now I think pretty much everything is fixed. So WNB, this is the train function, new function that we defined. Inside that function only we are putting everything. So if we now run this piece of code, no problem, nothing will happen because it's just a definition of the function. Now we have to define the agent. So WNB.agent, and we need to have the sweep. Where is that? Sweep ID. And the function name is train. So function equal to train. Let's run this. I hope the syntax is correct. Yeah, so syntax looks correct, but I'm getting some sort of broken pipe. Okay, some sort of error is there. Let's see what is this. Yeah, I don't think none of our calling WNB login after WNB.init has no effect. Agent has started to run. I don't think we are calling WNB.login anywhere, right? Am I? Yeah, I don't think I'm calling it anywhere. I'm not sure. Okay, so this one looks like it's running, but we can check the weights and biases. This URL to see if everything is if something is getting logged in or not. All right. So this is my dashboard. If I refresh this, hopefully we'll see something. I'm not sure if output will be there or not. Let's see. Okay, these are the different sweeps that are being visualized, but okay, now no metrics have been logged in yet. So I'm going to just interrupt the execution for now because I'm not sure if this is running at the moment or not. Maybe we can start this once again. Maybe I can give a new project name. That might be better. All right. So like this, we'll run the first cell block. Then the project name could be new version 2. So this will create a new project in weights and biases because this project does not exist. So it has created a new project. Now I think I can run the whole thing again. So I don't think we are mentioning the project name anywhere else. Yeah, I don't think we are mentioning it anywhere else. So it should be fine. And function equal to train sweep ID. So now, yeah, I think now it's running properly. So here you can see user warning, do not pass. Okay, name batch is not defined. Let's see. Oh yeah, that is the error. Let me interrupt. It's not bash.epoch, it's config.epochs. So that is one of the issues. So now I can run this once again. Okay, I hope now everything should be fine. Yeah, now I think it should run fine. So epoch 1 out of 5, accuracy loss. So it's working fine. So now it will do a proper sweep of different configurations. And let's go back to our dashboard and see if in the project something new can be seen. So the project name now is not 5 flowers new, it's 5 flowers new version 2. You can see it will get updated. So in the dashboard here, yeah, so now it has started to get updated. This is not accuracy versus loss. It is each step of execution. Here, actually, you can add plots according to your wish. So now what I'm going to do is let it populate these results. So see, it's getting updated real time. So I'm not doing anything right now. The Google Colab is running. Whatever output is coming out of Google Colab, it's getting logged in here. So this gets updated real time. And these random names, fresh sweep 1, wise sweep 1, all of these are random names for different experiments. You can name it whatever else you want to name it, no problem. That I hope there is some settings for that, but so far it's fine. We can, in the plotting, I can show you how to change the name in the legend of the graph. So you saw this graph getting updated, right? So here you can see learning rate is 0.001 for this current batch of execution. Accuracy here you can see, loss you can see. Now what I'll show you is, let me go back to this project, 5 flowers classification project. So this is the run which I had already done earlier. And what I'll do is, first let me delete all of these things. So what if I did not have this graph? Because I created this manually. This was not existing. All right, so nothing is there, no visualizations yet. These are the default things which were logged in at the end of my experiments. Here, there are 45 experiments which were visualized. Okay, so here let me minimize this epoch, batch, and system. So system is something which usually I don't think you will run into this network traffic, disk utilization, etc. This may or may not be useful to you, but not for most of the beginners. Here it is running versus for various epochs, as you can see here. And I'll show you why this is not showing 5 because you are running either 5 epochs or 10 epochs, right? So click add panels. In add panels, click line plot. And in line plot, you can define the X and Y axis. So here, let's say it is per epoch, you are looking at epoch. So, so epoch slash, you're looking epoch wise. On X axis, you want epoch value only. And then on y-axis, you are again looking epoch wise, but you want this thing, validation accuracy. All right. So these are the validation accuracy of various experiments. How many experiments? Just the 10 experiments, because here the setting max runs to show is 10. So these are those 10 experiments, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. But here you can change this to 50 or whatever number, maximum up to 50 is possible. So here you can see now all results from all the experiments are there. But you see, it's like weird. It's very hard for you to understand which like what is the super sweep 29. So let's say you want the legend to mean something. So these are the legends. So you can click the legend, and instead of name, let's say you want to compare the results of the experiments with your hyperparameters. So you can just create the legend by using hyperparameters as the name. So first hyperparameter could be batch size. Second one could be epochs. Third could be number of hidden units. Fourth could be what else? Image height. And fifth could be learning rate. So these are the hyperparameters that we were controlling, these 5 ones. So here you can see that the legend has also changed accordingly. So this is the way you can read this graph is, so this green color graph, which is now highlighted when I move my mouse pointer here or here, it has 8 batch size, 10 epochs, 128 hidden units in the hidden layer. I hope you can read this. The font is too small, I know. I wish I could change it a bit easier. Let's see. Oh, where is my panel? My panel has disappeared. No problem. So this should be epoch slash epoch, and y-axis I will put epoch slash validation accuracy. And okay, only these 10 graphs are enough for now. No need to complicate. So legend, in the legend, let me put batch size, epochs, hidden units, image height, and learning rate. That's enough. And then I'll apply this so that this graph gets saved here. Okay, so now the graph is here. So if we expand, if we want to see this full screen, click this expand, and now this is the graph. So if you want to see what are these parameters, I think all you need to do is like click this. Click this. So I click the legend itself, and then here you can see the that particular experiment. So in that particular experiment, we ran around I think 9 epochs or 10 epochs, 9 epochs, I guess. And the validation accuracy has gone until slightly above 0.5. This is the loss for each batches. You can see the learning rate was 0.001 in all of these experiments, and the accuracy batch wise also you can see here. But let me go back to all the runs. So there were 45 runs here. I'm just showing you how to read the experimental results. So now this is the graph that we just plotted, and in the settings. So let me take a screenshot of this legend so that I don't forget. So first is batch size. Okay, we can see it here. First is batch size. So batch size 8, 10 epochs, 128 hidden units, image height is 32, and learning rate is 0.001. Here in the next graph, it is 0.0001 is the learning rate, but batch size, epochs, hidden units, image size has also changed 16. So you can see all the parameters, and you can plot up to 50. So here, let's increase this to 50. Then you can see other experiments also. So when we apply, you can see that in some experiments, epochs are only 5. In other experiments, epochs are 10. So these graphs, these dotted lines are the ones with smaller number of epochs only. So here the count starts from 0. So 0, 1, 2, 3, 4. So total 5 epochs. And you can see the accuracy. And here you can actually compare. Here the best graph with the best validation accuracy is this green one. It has 0.52 validation accuracy. The one with the worst is this one. It has 0.44 validation accuracy. And this is how you read and compare the different models. So you can also exactly just read from the legend what these what is the hyperparameter difference between this green graph and the red graph. And if you are a professional, even if you want to do something serious as a student, you should use weights and biases or similar platforms which will allow you to conduct these experiments. Meanwhile, let us go back to our 5 flowers new version 2 project and open to see if more experimental results have come. So here, see, the last run was 2 seconds ago. So definitely new results are going to come here. Yeah, so 3 of them have been visualized, 3 of the runs, and you can see that here. Okay, already I think we can add a new plot. So let me add a line plot which shows epoch versus epoch on the x-axis and validation accuracy on the y-axis. And oh, so far only one iteration has been finished, is it? And maximum 50. And in the legend, I don't want the name. I would rather want batch size, learning rate, image size, hidden nodes, and epochs. And if we apply, and this graph will get automatically updated. So currently the first model is yet to finish running. We can go back to the code to see that. So here we have only finished 3 epochs, so it will take time to log more data points there. So right now the 0, 1, 2, 0, 1, 2 is finished. 3 is yet to come. So that is why I think if we refresh, maybe 2 also might come here, but that's it. So what you can do is you can run the same code. I will share the code with you. Do run the code and try to create an account in weights and biases. So all the next lectures, in the upcoming lectures, what we will do is we will only be looking at weights and biases to compare the accuracy of different models, or compare which hyperparameters are making our model the best, right? So here you just saw it real time got updated. So let us do this. And also you can create beautiful reports, by the way. So if you want to create a report based on your experiments, all you need to do is like go to your particular project. So here the project's name is 5 flowers classification. Click new report. And in the new report, you can decide which all plots to include. So if you want to include all the plots, you can click all of this. I don't think system plots are really needed. Then click create report. And this should create a template of a report with those plots. And then you can add more information. Like you can write 5 flowers data set, experimental report. And then you can add whatever description, and you can put name. I don't think Sridhar exists in this team. And then here you can type, there are many more things which you can include to make this report very comprehensive. And once your report is ready, you can also publish this report to the project so that whoever is part of the project can see the report. And I think there is also a way to make this visual, like visible to others. I think there are ways to make your project visible to other people. Let's say anyone in the team can view, or anyone with a link can view. How about this? I think if we use this and if we copy the link, I think anyone with this link can see the report. So this is a great way, and this is our interactive graph. This is not even static. So they can hover over this graph and see all the things. And here, when I hover on one graph, it highlights the corresponding experiments in the other graph. Do you see that? When I'm moving my mouse pointer, it's highlighting the corresponding experiments, not just in this one graph, in all the other graphs, because all these are different graphs for same set of 45 experiments that we ran. Although here 45 experiments are not being plotted, I think only 10 are plotted. Here alone, I'm plotting all the 45 experiments, but these are only those 10 experiments. We can decide which 10 experiments we want to plot, because this is obviously less readable. This is more readable. That's why. So you don't want to make your graphs crowded. But I think that is a very good introduction to weights and biases. I hope you understand the utility of this. I hope if you want to seriously do the hyperparameter experiments in the rest of the course, because in the next lecture onwards, we'll be doing more number of such experiments. We'll be changing dropout rate. We will be introducing regularization. So all of these are different things which we can do to try to make our models better. Right now, our model accuracy is still at 0.5, 0.55, that range. It's not 0.95. So to take our model accuracy to 0.95, there are certain things that we have to do. Maybe we'll have to do a transfer learning. And of course, to prevent overfitting, we'll have to do a bit of hyperparameter tuning, introduce dropout, introduce regularization, etc. So all of this will be so much painful if you're going to do it manually in your Google Colab. So do it with weights and biases. So I'll be following this method. But I really hope you enjoyed and you understood this whole idea. And I'm looking forward to meeting you again in the next lecture to implement all these things for our upcoming models for the 5 flowers dataset. So with that, we come to the end of today's lecture. I once again would like to take a moment to congratulate you for finishing the course till this point. You are at probably the fifth lecture plus the introductory, so totally 6 lectures, and we still have many more actually lectures to go. But you should feel very good about yourself. You should feel proud that you have come all the way till here. It's very difficult to follow the course throughout till the end, and I know that many people are following it. Many people are hopefully diligently taking down notes. So if you have amazing notes, feel free to share it with others. You could even create like a public overleaf document which serves as a note for this entire course. So you can share the link in the comments. So there are many ways in which you can enhance the learning experience for yourself and also for your fellow co-learners. But thank you so much for listening. I hope you are implementing all of this as you are learning in this course, because there is no point in looking at someone else write the code, right? So you have to do this yourself. So if you have first watched this video at the moment, so far you have not coded, now you can restart the lecture and pause wherever you need to pause and write the code yourself. I'll be anyway sharing the code with you in the description, but I would love to have you write the code yourself and experience this yourself. Create your account in Weights and Biases. If you are facing issues, put in the comment. And I'm looking forward to having you upgrade your ML model running pipeline and ML experimentation pipeline. It will really make you feel like more powerful than what you feel right now. Thank you so much. We'll meet again in the next lecture. Take care until then. Bye.